Okay. We'll pick up from yesterday. So yesterday we actually construct everything. We construct the stiffness matrix, we enforce boundary conditions, we construct fixed end reactions, we put everything together, we solve for these structures, we came up with the displacement solution, we came up with some support reactions. Support reactions we obtain majorly in penalty method, that we just use the small deformation at the support multiplied by the spring stiffness, we end up with reactions. By Lagrange multiplier, as we have the additional equations that impose the condition of your displacement, right? Then we have additional unknowns which were the reactions. So once you solve for the displacement degree of freedom, you also have the support reaction as your byproduct. So it comes out just immediately and automatically. But up to this point, this is not enough for us to conduct structural analysis, structural design, let's say, because the analysis procedures was complete. But you don't use the U1, U2, U3 for your design. Well, you may have some support reactions, but still you need to find internal forces in your structural members. Well, keep in mind that this structure is a simple one. You don't need any transformation, so one step is still missing, and then I'll be covering it up in the maybe next problem. So first of all, let's come back to the row and column eliminations. We have at the first, you can see that in row column elimination, what you end up with is just only the displacement solution. That's all you have. And from that, you need to compute first the support reactions. And then you can find other things later on. But how to come up with internal forces and support reactions? So if you recall, when you construct the system of equilibrium equation from an individual element, you start with the equation that governs only one member. Even the beam or the truss member, it is just the governing equation for one member, right? So if you come back to that equation and then you stuff everything in, you'll be able to find forces that are acting at the nodes, at the degree of freedom, right? That will be the forces you use to come up with the internal force diagram, for example, shear force diagram and bending moment diagram, right? So we come back to an individual governing equation, equilibrium equation of individual element. So I copy this thing and then I come somewhere over here. I just paste it temporarily. So we come back to element number one. Element number one, you have this. So I'm gonna copy this, put it somewhere here. This is your stiffness matrix. The force will be on the left, F1, F2, F3, F4. Basically, you have the EI over L scale in front over here. U1, U2, U3, U4. Okay, I cleaned it up. Then U1 is 0, U2 is 0, U3 is also 0, and U4 is this quantity. Right, so now we are coming back to that fundamental equation again, but we do it one by one. You can find F1, F2, F3, F4 being equals to the stiffness part multiplied by the known the displacement solution we obtained before, right? And then what else that constitute this equation? Friction reaction, right? So add it in. If you have the temperature effects, creep shrinkage, that's gonna be in here. And keep in mind, this is without transformation. So if you have some transformation, then you just incorporate the direction cosine matrix in this equation. That will be just it. So fixed end reaction is here. So I put it there. Okay. Basically, previously we scaled the force equation by L, so we end up with the unit that is consistent throughout the 4 equations. Force by L, you get the moment equation. This is moment, this is force multiplied by L, and this is moment. So that's why we can pull out the EI over L out there. And that's why this is just EI over L, because you scale by the L, right? Is that all? Yes. Which is equal to this is equals to matrix multiplication of this one and this one, and then you add it up with this one. Control and enter. Okay, so the unit here is EI over L, or if you want, well, we don't want this, right? You want this. It turns out to be, so I copy and paste, square. Right? Force turns out to be in the force unit. This is in moment unit, force and moment. So we can write this down. Well, first of all, maybe it's a good idea to do a little check if it is consistent with others. We can come here, right? Lagrange Oh, and that is displacement, right? Okay. Here is the reaction force at degree of freedom number 1, reaction moment, right? Over here, this is R3. You find something different. You have 6 something, but that is 9 point something. Why? Because right now, it is the reaction force that acts on member number 1 only. But at that support, it produces reaction to member number 1 and member number 2. You look at here. What we obtain just now, we calculate the reaction to this member. So, the contribution from this member to this support is not included yet. That's why it was only 6, it's not 9. So hopefully when we finish up the next section, alright, the next element, it will add up to 9.9. Alright, so keep the finger crossed and believe in mathematics and science. Okay, so this looks good. This one we don't really have the moment reaction for the number 4 because it is continuous. We don't have the moment restraint at the support. But this minus 7.45 shall be equal to the on the just the nearby element. So the moment that is acting on the member number 1 has to be identical to the moment on member number 2, but on the opposite direction, so they balance, they equilibrate the system out. Okay, so this is for the first one. Let me do a little drawing over here. So this will just represent the okay, 5 point something, okay, 6 point something. What else? We have the moment is in the counterclockwise direction because you get positive, right, moment. So from your positive moment, there you go, you get this one. Seems a little too big. Okay, and then on the other side you get the negative. So let me, so it is clockwise. Okay, reduce it down a little bit. Aha. Oops. What? Jeez. No. Okay. I just addressed the direction of this moment already, so I will not put the will not keep the negative sign there, right? Okay. So here's what we come up with for the member number 1. We're gonna proceed to number 2. So move down here, member number 2. I'm gonna pick this up, copy, and then paste it here. Keep everything like that. delete everything out and clear this up and multiply by something like this. Okay, so you follow the same step like before. Now we have forces for F3, F5, F4, F6 are the moments. You're gonna multiply with, alright, so what do we have in here? Number 3, 0, yes. Number 4, 2 point existing. Number, what else? Number 5, this. Number 6, alright, 3 points, okay. 4, 3, 4, 5, 6. Now, let us look at the fixed end reactions. We found that on this member, we have nothing applied on this member. So fixed end reaction turns out to be 0. Okay. And then, let's do the solution. Let me check if it, okay, it does. So we have this solutions, and then here we get not necessary. And just copy this. Okay, there you go. So if we want the support reaction number 3, then it is equal to F3 plus F3 there. Okay, we are happy, right? This is so satisfactory. What else? You can see your F4, which is equals to 7 point this, as you don't have any applied moment at that degree of freedom number 4. Then 2 internal moments has to cancel out. So this is clear. Now next, F5. F5 is the force at the hinge. So this is the hinge force. This is a force which is coming from the member number 3 that acts to member number 2 through the hinge. So the same force magnitude but on the opposite direction will be acting back to member number 3. So we will looking forward to see the same force magnitude for number 5 and number 6. Why do we have number 6? We have a hinge, but at the hinge we have the rotational spring attached. So the relative rotation between two sides, between two members, will produce the bending moment across the hinge, right? So that's your stiff springs, your moment you receive over here. Can we cross check? Yes, we can. How do we cross check? We have the rotation U6 and we have the rotation U8. Okay, so the relative rotation U6 and U8 will produce the moment. That relative rotation multiplied by the stiffness, rotational spring stiffness, it should be equal to this moment. So let's see. F4, okay, F5, F5, okay, hinge force, okay, F6, alright. Then we come to the next element. This is the most logical situation you have. Well, I'll be doing this, copy the whole thing. And this is F5, F what? 8, right? Because we replace the number 7 by 5. So this one's got to be F9 and F10. 5, 8, 9, 10. Then the entries in the matrix, we have this being this one, this being this being this one, and this is this one. I copy this, copy this, and then copy this and this. Okay, there you go. And then in here, let me move these gangs down here. So I need the U5, I need U8, I need U9, which is 0, and U10, which is 6 something. So this is equal to, oops, sorry, this is the fixed end reaction, so this one and this one. Okay, so we get this. Is it? The sign. We have this apply. Wait. This is the vertical force. F5. Wait a second. Where the sign was supposed to be. It is here. Sorry. So I just compare with this one. This one is F3. Okay. Now F5 acts. This one acts on the member number 2. This F5 acts on number 3. Okay, yeah, just confused myself. It's just by accident that the magnitude is just accidentally the same, so I just, okay. And this is what, F5, 8, 9. And F10. Okay, so now it is beautiful. This one is identical to this one, just opposite in the direction. This moment is identical to this moment here on the opposite direction, well, due to that rotational spring. In order to do a little cross-checking to find out if it works in the way that we understand. So if we just compute the spring force magnitude by taking the rotation, which is this one, minus this rotation, right? This is the rotation at 6 and at the 8. So the relative rotation between these 2 points give rise to the moment from the rotational spring. Right? You have rotation on 2 sides of the hinge. If they rotate together at the same magnitude, you don't get any moment in the rotational spring. But once they rotate in a relative, okay, at the different magnitude, then that causes you some moment. What was the stiffness of this spring? It is 10, right? Okay, multiply by, then it is multiplied by 10. This 6.9, right? It is consistent with the calculated moment which is acting on the member. Now move forward, so we come to the F9 and F10. F9 is a support reaction, but again it is just on one side, so you have another beam that contributes to this support reaction. We are calculating effects from this beam, so it has to be add up with the effects from this one, and also the 10 moment number 10 here will be equal to the next beam. So I clean this up. I just maybe copy this. All right. So F3, which is this one. F5, this one. Moment, this, and well, and another moment. I put it here. Okay. Basically, it is very easy for you to look at. You have take a zoom out. You have this point being this one, moment. Reaction force adds up. Right. So if you draw this, basically you will need to do this because I think the sign has to be okay. I'll fix the sign a little bit, but first of all, you have to draw this. Once you draw this, you have this shear force, this bending moment, and then you can continue from this point in order to elaborate the diagram on individual member. That will be the step before you design the cross section for the RC or for the steel. You have the pattern of the internal force diagrams. Positive go up, positive this direction. The 6 is supposed to be I think that there's a okay. I can flip it over because the moment is positive for here, for this one, so it has to go this way, and shear force is negative, right? Okay, and then I clear out the sign. Then let's do something with this one. The same thing. F5 going upward. This one has to be flipped. Oh. Okay, clean out that 11 has to be here. Flip it up. This is just a cosmetic. You may not really have to do all of this, but well, it just make your work neat. Okay, so positive going. Hey, wait, yeah, this is negative, so it goes clockwise. This is negative, so it goes clockwise. Positive go up, positive going up. Okay, yeah. Move forward to the next one. So we have this one here. This is equals to this, and then copy and copy down. Who are there? 9, 10, 11, 12. 9, 11. Okay, and then we clean this up. We also clean this up. This is from the fixed end reaction. This one I move it down to use here, and we need the 9, which is 0, the 10 6.2, the 11 is 0, and the 12 is minus 4.7 something. Okay, alright, stiffness matrix done. Displacement solution, substitute. Fixed end reaction is there, so these are okay, the product from here. And then I already, okay, no, jeez, delete that, always complain. Okay, and there you go. I copy this down to use over here. Okay, then if you recall, you have 19 over here for the R9. You come back here, you have F9 11 add up with, sorry, here. Okay, so R9 is equal to F9 plus F9, and there it is. Okay, match, perfect. The 10 and the 10, you can see they are identical in magnitude. Well, later on, if I put some moments like this, if I apply moment at the joint like this, two sides will not be identical. So the difference between two sides moment will be equal to the applied moment from the external. Okay, that makes perfect sense for now. 19.6343 come here, 6343. Okay, match. So we need the diagram here. So let me put things in. This one, 12. It's gotta be this one. We're gonna reverse it. And this one, negative already. Okay, it has to be clockwise. This one supposed to be counterclockwise. There you go. 12. Okay, opposite. 11 add up with 8, you get R9. Okay, so move to the next element. And it is 11 to 14. So paste and paste things in here, delete. Okay, multiply by L and multiply by L. That's it. Oop. So here we need this one. No, we cut it. Oh, cut and paste here. F11 is the support 0. F12 is the rotation. F13 is the spring. So it is settling down, and the last one is a rotation. Add up with the fixed end reaction of this member, you get all these things. And this is here. First thing, this is very beautiful. You get 0 at the degree of freedom 14. You don't apply any moment, and it is the free end. It is a hinge end. So you get 0 as it should be. At the end of this class, I just hope that you have a faith in science and math more. Yes, sir. I thought that you call me. Okay, no, all right. So this one here, moment has to be there, and reaction from your spring is here, and moment is got to be there. Positive, correct? Positive, this is 0. Okay. 8.8, yes, identical, but on the opposite direction. 6.7 and 10, we can calculate the reaction. Boop. So the reaction R11 is equal to F11 here plus the F11 there, enter, 17. Okay, I'll move it here. Office. Well, 17, right? There you go. If you remember, we have the hinge force from Lagrange multiplier being 3.60. This is hinge force at degree of freedom 7. That means hinge force that is acting on member number 3. Because initially, if for that Lagrange multiplier, we set up H7 being this one. So it is acting on member number 3 at the hinge. Come back here. 3.6, right? You can see this 3.6, but the 3.6 positive is acting on number 3, so which is this one. So it is minus 3.6, which is F5 or H5 acting. Well, you set up H5 being equal to minus H7 last time. And what else? 7.5. We don't have that in Lagrange multiplier. The spring force in the the reaction from that spring force on the degree of freedom number 13. So it's okay, but in fact, if you want, you just multiply the settlement at the spring by the spring stiffness, and it turns out to be this one, which has to be identical. So let's see, spring support. F13, right? Spring force. Okay. Spring force, you need this one, 13, multiply by what's the spring? I think it was 40, right? And you need the okay, you need the negative sign. Yeah, that's it. Feel very good. This is rotational spring. All right, so we are done. This is the complete procedures for the structural analysis from the very beginning, setting things up, all the way to the solution phase. You obtain displacement solution, and then to the internal force interpretation. So this is the post-processing procedures. We will do exactly the same thing as row and column elimination in penalty method and also in Lagrange multiplier. The internal force diagram, I think I don't really need to cover that, right? I think the SFD and the BMD are quite a simple thing. You can do it for yourself, right? I will not go down to that level too much. Up to this point here, I think it is good enough. Actually, if you, well, I have my own spreadsheet. I don't use it much anyway. But if you write up your spreadsheet and then you need the input for your spreadsheet like this, so it is like fixed end actions on your member, and then you have the force function over your member as like an input, and then it can generate the automatically it can generate the BMD and SFD. So you can put like the profile of the uniformly distributed load, or maybe the distributed load but not over the entire span. You can put point load, point force, point moment, etc. So the program, the spreadsheet is capable of dealing with many types of load, right? And once you finish the structural analysis, then you just put this result at the end into your spreadsheet and input the information about load. Then it generates the SFD or BMD automatically. So that could be useful for your design, because in structural analysis program, the last part might be over here. I think in SAP you can click and see the internal force diagram for each individual member, right? But well, sometimes if you want to just extract this information and use along with your design spreadsheet, that could be a good tools for you. So now let's take a look at the solution we obtained from penalty method. You will carry out exactly the same procedure. So you will use this stiffness matrix, which is exactly the same as the one before in row column elimination. What you have which is different from the one before is your solution. So U1 is not zero. You need to just put this in. U2 not zero, U3 also a non-zero value, and U4. So you put all of these into the setup here. You come up with the force actions at the degree of freedom. It has to be pretty much identical to the other technique. What else do we have to concern? I think most of the things are identical, but okay, I taught you already how to come up with the reaction force at the penalty spring, right? So there will be nothing special over here. We cover pretty much everything already. You can try, you can do it. So follow these procedures, you will end up with pretty much the same thing. Minor difference, as you can see that we had some error of part per million by using the penalty spring. Something might be the concern generally for the structural analysis. The problem that I mentioned yesterday about the large number that you put as the penalty spring stiffness, that will make the condition of the matrix, the condition number of the matrix seems to be quite large, and that means you are quite like a singular matrix. You cannot inverse it. Okay, the problem like that come up, but you don't find in general for structural analysis. But for finite element analysis, especially when you have like different element size, like some area you put a very fine mesh, small element. So very small element, your stiffness will be extremely high when the element is small. It's like if you discretize your bar member into small size, so the EA over L that control your stiffness, EA will be the same, right? If it is a constant cross-section bar but you discretize somewhere, okay, into the very small L. For example, if you discretize to L being the length being 1 in 100 of the entire length, whereas the nearby element is 0.99 L. So the stiffness you obtain from two members is approximately 100 times different. It could be worse and worse and worse as you have the more and more difference in size of the member. And in FEM, in some hot spot like the stress concentration zone, some spot that you apply the point force or the sharp corner, you expect the stress concentration. So the fine mesh will be required to pick up the result, the solution which is accurate. So it is not special, it is generally can be seen in FEM. So the different mesh size is expected in some problem. Some area that you don't need too much, well, so much accuracy, then you just use a big mesh. So that difference could be leading you the problem to the issue I mentioned about the ill condition matrix. But in structural analysis, generally you don't discretize member like that. Very small member like 0.01 L and 1 L member just nearby. That is not generally not, you cannot see that. Lagrange multiplier. If you come back to Lagrange multiplier again, you put all of that operations on the side over here, then you can figure out F1, F2, F3, F4 by substituting the U1, U2, U3, U4. So these procedures identical. Okay, no matter what technique you use for to enforce the boundary condition, but this fundamental equation of F equals to Ku plus the fixed reactions has to be usable. Okay, then how do we move forward? I think maybe at least we can talk about the homework, right? So let me bring you to my iPad. Just a bit. Okay. I mirror the screen. Is it connecting to the internet? Huh. Or not connect to the internet or what? One second, let me connect. It doesn't ask me, well, anything. It is on the same network. Oh, come on. I cannot find the iPad from this network. This is okay. So I will just write up the problem for you, homework problem for you over here. Oh, actually, it is a good idea to do it over here. just random. Okay. First problem, you have just randomly put it in 1, 2, 3, 4, 5. I'll send you this file, so don't worry. Just random. Okay, make something challenging for you. And then okay, some monster in there. What else to make it cool? Spring. I'll try to make a beautiful version for you later. This is the ugly version first. Okay, this spring, which is the translational spring, is attached to this side of the member. This monster is, well, a brother or the sister of the hinge. Hinge transfer shear. It doesn't transfer moment. Okay. This one transfer moment, but not the shear. Okay. Well, I didn't put the relative translational spring between these two, so it doesn't really transfer shear. If this spring, one end is on this side and the other end is on the other side, then you need to construct the spring element like before. But this time the spring is supporting. Alright, so it is a spring support. But the spring support is attached on just one side only. So it is just 1 degree of freedom that is associated with this spring. The degree of freedom over here, the displacement degree of freedom here, does not have anything to do with the spring. Alright, it is free. But anyhow, the moment is coupled. So same moment, it transfers the full moment to the other side. Alright, and then let's see what could be done else. What else? I apply moment over here. So essentially your force vector on the left hand side that used to be just 0 and some other reactions, now you have those 0 non-zero, right? So we apply moment here, maybe just more than one. Oh no. Okay, I'll give you the moment magnitude later. And then what else? And that's gonna keep you busy for a while. There you go, point force. Okay. In the exam, I give you a problem. I may not, or maybe I will not. Okay, I'm not give how the degree of freedom, the setup of the degree of freedom. Let's talk about it this way. That means when you see the structure, you should be able to plan and set up the degree of freedom strategically, all right? That must be consistent with the analysis scheme that you use. So you need to write it down. First of all, the one that you cannot miss in the exam, you need to show me how you set up your degree of freedom. If you don't do so, I don't understand your work. And if I don't understand your work, you cannot come back after the exam and explain your work at my room, because that is not fair to your friend, okay? Don't walk to my room and say, sir, and point the finger to your paper, here I did this, because your friend, they do not have the chance to do so, to do the same thing, okay? So there will be no explanation, individual explanation like that. All explanation must be in your exam. Your answer paper is self-contained, all right? No more than that. That means the things I mentioned yesterday, like you have some star, some sharp, that because your figure is just running out of the space, so Excel just show that kind of thing. You just switch around the page, okay? Spare like 15 minutes or 10 minutes at least to check your work before you submit your exam paper. Not like, okay, you have 10 minutes, you still do things like that, and then time's up, then you just staple everything and then send to me. Submit that thing to me, and with the 10 page on the first page on the last, things flies around, I don't get the sequence, all right? If I can try to understand, I might take some course. Well, it has a course to facilitate you, right? So if you switch things around and put me in a hard time, the more time I use to grade your work, well, the more frustration, and then the more frustration, then the less point you will obtain. So make sure that everything is in the sequence, in the form that is ready for me to understand. You may not just submit Microsoft Excel scratchpad like this. I call this scratchpad, even though I think I do it in quite a neat way, but it is like a scratchpad to me, all right? So you don't submit it this way. I will not just look around and find, oh, you find reaction here, oh, you do it this way here. You need to explain. Maybe if you have to print it out, generally I will ask you to print out in PDF, submission in PDF via email. So you must be able to connect to the internet at the end of the class, and your computer must be able to print out the PDF. So don't ask how to print the PDF from your Microsoft Word or from Excel. You can do many things. You can print out from Excel directly. You can copy this screen and then paste it in Microsoft Word, and then you do the explanation like, okay, here I set up the stiffness matrix, element stiffness matrix for what? For the member number 1 and etc. You combine the system stiffness matrix, then you explain, and then you find action forces on your degree of freedom. Then you explain, okay, you do it here, you do it here, you do it here. It is perfectly okay if you want to make sort of like the format to save your time, like, okay, you know that this is going to be the flow, so you will put things in Microsoft Word like calculation of stiffness matrix for member number 1, 2, 3. Okay, you prepare that sort of format, and then when you work in the exam, you just snap the screen and paste, snap and paste, snap and paste. I can follow that. Okay, you can prepare that ahead of time. Fine, your computer, you prepare everything you want, right? You bring it in, you just disconnect to the internet for like a few hours. But further than that, you have the freedom to do anything with your computer, okay, aside from communicating with people via the internet. So you can prepare, right? But the ultimate goal is that I open the file up, I'll be able to read it, I'll be able to understand it, and if I cannot find any piece of information I need, you might put there, but you put something like just this, maybe the thing in this, I don't know, this is for which degree of freedom, right? What is this, fixed and reaction, or what, or left hand side? I have no idea. You do it, you understand it, but you don't explain it to me, right? So please prepare, spare your time a little bit for explanation, put things into the right sequence, PDF them into just one file. I hate to like, oh, you have 5 files, I got to open here and there and there and there, okay. And yeah, practice a little bit before the exam so you know how to deal with your computer. I just don't want to be like a computer guy to fix your computer in the exam. And you cannot ask your friend, hey, can you come and fix it? Because your friend has to do something he or she is working on, right? So prepare all the things. And yeah, that come back to that degree of freedom. So you need to draw it and specify precisely, this is U1, this is U2, U3, U4, U5, etc., etc. If the setup of degree of freedom is incorrect at first hand, at the very beginning of the problem, I will not grade. So that is automatic 0. Alright? I will not grade because if you cannot model the structure correctly, that is the beginning of the disaster. You, no matter how well you do in the RC design, steel design, stability issue, etc., but you put the wrong things there, the wrong boundary condition, wrong hinge, wrong displacement degree of freedom, then it is useless because the setup is the most important. All right, spend time, think, and relax. I mean, don't get too excited. All right, calm down. Once you open up the exam, well, you will get the first shock anyway. That is normal. So it will shock you. At the first moment, you will feel like, whoa, what is this? As it is video recording, then I cannot put the full version. Okay, so it is just, what is this? I would like to put the more colorful version of this, but yeah, it will be on the YouTube. Okay, I'm afraid that it is not appropriate for the education video. Alright, but take a deep breath, relax, Okay, you got to do it anyway. You cannot run away from it. You cannot just wake up and find that it is the nightmare, all right? Because you will never wake up from that. Okay, it is the real thing. So just look at it carefully. The better you set up things at the starting point, the more chance that you will finish everything's up successfully, right? So spend time thinking about the concepts from very first class. Generally, I will just bring you to the very first class. I use everything I talk in here and put in the exam. So calm down and you'll be good, right? Sometimes it is ridiculously easy, but at the beginning, if you set it up in the wrong way, then you just get lost into Amazon jungle and then you never come out because you are eaten by the crocodile or anaconda there. But it is actually as easy and as beautiful as the garden on the backyard if you just walk to the right way, right? So spend a little time thinking carefully about the strategy to solve the problem. So set it up in the right way. Just that. Here, okay, I can put many things in here, right? 3EI, and what is how many L? 1, 2, 3, 4, 5 L. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8. 4EI and 8L. This is a hinge support, okay? Pin support. The beam is a continuous beam, right? I didn't put any rotation, the release, the moment release at the support there, so the moment can be carried over to the next span. This is 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Okay. 4EI and 7L. 1, 2, 3, 4, 5, 6. 2EI and 6L. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5EI and 10L. Now, well, let us apply the load. Uniformly distributed load. Oh, and one thing, you don't really have to redraw the structure. Sometimes you draw the structure I have in the problem, but just waste your time. You don't get any extra score from that. So I draw this to you, and then you redraw this thing in your exam paper. Well, I can interpret that into maybe I think of that like you have no idea what to do, so you just redraw it, but you don't really have to redraw it, okay? But you need to put this in the degree of freedom setup in here. Okay, we have the applied force like this. Previously, what did we use? 3EI over LQ. Yeah, just make it 2EI over LQ. This is the magnitude of the distributed force. I make this one and this one. Okay. The magnitude here, I'll make it 5 EI over L cubed. The force here is equal to 5 multiplied by 8, you get what, 40. I just make it 20. Okay. Point force 20 EI over L square. I have to think of the spring stiffness. I feel like I want to put the spring over there. Yeah. Just to give it a help. Let's talk about moment. Moment here will be over L, but it's 20 to yeah, 30 EI over L. And this moment here is 50 EI over L, 50. Well, okay, not bad. What else? Spring stiffness. Spring stiffness will be in the same unit as this one. Force per unit length. I'll make it 200 EI over L cubed. And this one is 100. Okay, so you have the spring force, you have the external force applied at the same point. It is quite a good exercise. Okay, over here. Over there, I'll put more force there. Actually, this doesn't alter anything with your analysis solution, because it is the force which is concentric to the support location, but it will change the force at your support. Okay, it is just right above the support. So rotation displacement solution will not be changed no matter how you change this force. But when you calculate the support reaction will be affected by this point force. Maybe one more thing. 10. So this distance is what? 3L. What else do we need from this buffet? Okay. Yeah. Okay, it is a buffet. Okay, buffet of structural analysis. It has everything, all you can eat. Moment, has to be, stiffness has to be just something like this, 10 EI over L. It is in the moment unit per radian. Radian has no unit, so it is in the EI over L unit. Oh, good. Looks like a very good exercise for you. I need it done. First of all reactions, all displacement solutions from U1 all the way to U something. I have no idea how many U's you have here, but so let's count together. That makes the grading easier. Let's count. But in the exam, we will not count this together, right? You will count that alone. Okay. Right. Oh, okay. First degree of freedom. Here and there and there and there, and I'll give you this one. Narrow it down, make it smaller, and yellow it up. 1, 2, 3, 4, 5, 6, 7. What do you want to use? Maybe Lagrange multiplier. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Not more than the one we had before. How many conditions, if we use the Lagrange multiplier, we will have additional equations from? First, support condition here. 1, 2. You have the conditions that makes the rotation of these two, force them to be the same. 3, 4, 5. Actually, it's not more than the problem we just finished. 5 equations. Right? Now, you get displacement solutions. You obtain support reactions. All the actions on the individual member, and finish it up to the SFD, BMD. Alright, make it a complete work. So that is the point where you will leave off as a structural analysis point of view, and then you continue with the design procedures. So you finish all the way to the post-processing. In the exam, I will not ask you to do SFD, BMD, but for the sake of learning, I think you can just revisit what you used to know in the past. First problem. You have the second problem. The second problem, as I used to promise you about the no, I will not put you in the crazy thing like that another time. I have this. We used to talk about this. We used to do this homework. So one, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, but 12. Okay, and make it 6. 1, 2, 3, 4, 6. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, good. So, what is going to happen to you? I'll take this, oops, and this, bring both of them down to here. Okay, so we used to develop the stiffness matrix of this member, beam member, with the varying EI value. So I think we vary from 2 EI to 1 EI on this side, on the right hand side, and you evaluate everything, the stiffness, rotational stiffness and translational stiffness. You have done it by the closed form solution. So you derive it and solve mathematics equations, so on. But now you have another choice. You can use the approximation. The approximation I talk about here is to just, okay, let me do it this way. So you can do things like this. Well, it's too bad. We will have 16 step, right? 16 step, then it's gonna be 32. Let me do it this way. 32. Okay, you have 32. Let me squeeze it in. And then, okay, so the beam will be simplified by this, like this. So you break one beam into 16 sub beams. Spend a little time over here. Is that 32 already? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11. Okay, whatever. It will be matched with this one. Fill, no fill. Line. Okay, thick line. Okay, I just simplify it so get some idea. Okay, right. So basically you discretize one beam into, I need 16 sub-beams. Out of these 16 sub-beams, you find the middle point of the sub-beam. And then at the middle point, you find the corresponding EI. Okay. And then you use that uniform EI to represent your member in that sub-beam, the small beam. I think so. Now you have one beam member, two beam member, 3, 4, 5, all the way to the 16. Out over these 16 beams, none of them have the same EI value because the EI keeps changing, all right, with the position. So this one, you find the EI, the EI at the middle of this, of this sub-beam. Okay, you find the EI at the middle and take that EI and put it into your sub-beam. This sub-beam is connected to another sub-beam. Another sub-beam, you take the EI value at the middle of this point. Okay, this here point here. Okay, you use the EI there, put it here, and then you have on and on and on and on. In total, you have 16 beams. Now, these 16 beams will be supported should we call it supported? Okay, we don't really have to put the boundary condition. The ultimate goal is to find the stiffness matrix by approximation technique. So you construct the whole system up. You have 16 sub-beams, that means you have 17 nodes. 17 nodes, you have 34 degrees of freedoms, transverse and rotation. Okay, these 34 degrees of freedom, you will establish one structural system. Okay. Then you will find the stiffness of this and turns it out to be just 4x4 matrix. How? First of all, you lock this degree of freedom, you lock this degree of freedom, you lock this degree of freedom. You can use Lagrange multiplier because at the end, when you solve everything up, you will get the reactions, right? That will be the force you use in your stiffness matrix, right? You will enforce this U1 degree of freedom. You apply 1 unit for your U1. So you apply the number 1 in there. You apply this in using Lagrange multiplier. We used to have this on the left hand side prescribed to 0, but now you can put the -1 in there. When you put the minus 1 in there, you have the 1 unit displacement apply to that degree of freedom, which is the degree of freedom you want. So this is a concept we use to come up with the stiffness matrix. We have one beam element at the second class. We displace the node, first node, to 1 unit deformation U1. You keep other degree of freedom stationary, 0, they are all 0. Then you get the corresponding force, moment. These 4 forces and moments are the function of that 1 unit applied displacement at the left end. Is that right? Then you continue. You fix this degree of freedom. You fix this degree of freedom. You fix this one. You apply 1 unit rotation. So you reset up another system of equation. You have to do it one at a time. Okay, so this is a new system of equation. You apply 1 unit rotation at the left end only, and then you will observe moments, force, moment, and force at other degree of freedom as well. This is the function of 1 unit rotation. Okay, and so on for this one and for this one. So you have 4 sets of equations. You solve all of them, you get corresponding reactions at 4 points. The other nodes in between, they are the free degree of freedom. They move freely. Alright, so you don't have to put any boundary conditions at the other nodes, but just the leftmost and the rightmost. So you will end up with 16 quantities, 4 by 4. 16 quantities. 16 quantities, you stuff them into the 4 by 4 matrix. And then compare this matrix with the matrix you obtain from the closed form solution. See how close they are. Alright? Just that. So 2 questions. Due Monday, not Thursday, not Thursday. Due on the next Monday.
So what's the name of this support?
What?
So what's the name of the hinge?
That, well, it's not a hinge. It's a roller, but it is not the support. It is just the roller connection, the moment restraining connection. I don't know what to call anyway, but it is one possibility. If you have hinge, then this is the brother of hinge.
If I want to find just the external reactions, can I just use the combined stiffness matrix?
Just external reaction.
Yeah. To solve for the reactions.
Okay.
What we've done is to use the matrix.
Oh, okay. All right. I get your point. This is the procedures that we do one by one. Okay. If you want to find, of course, you can look at this thing here. In this matrix, okay. In this matrix, your reactions are embedded inside this F1, F2, F3, F9, F11. You can come back to this matrix here, this setup. Okay, you use this set of fixed end reactions. You input, you substitute the U1, U2, U3 up to U14. That thing will be multiplied with this, add up with fixed end reactions, then you will get reaction forces and moments here. Yes, correct. It can be done. The thing is that this thing inside over here is a reaction. F1, F2, F3. You don't have any other applied force, but just the reaction. So things in red will be determined. Things in black are known ahead of time. So once you finish the calculation, things in black must match on left hand side and right hand side. The calculated right hand side entries which are associated with the black locations must be matching well. You can try. Why not? So I take the whole thing here on this side. Okay. I'll just get this cleaned up. Okay. I'll move this to the side a bit. Now, as well, at the support you don't apply anything. You have only reactions. So F1 can be called as R1, R2, R3 as a result. And then 4, 5, 6, let me obtain all of them. Oh, okay. The thing is that 4, you don't have to apply moment. No apply point moment. 5, no apply point force. 6, no apply point moment. Okay, so I think where is it? Is it? Okay, yeah. So we can 0, 0, 0, 0. Alright, they're all 0. Equal to this, which is gonna add up with this. Okay, I will not keep this, okay? You know how to fix them. We'll just take this up there. Okay, so U1 is 0, U2 is 0, U3 is 0, U4, you bring it up, U5, U6, U7, we don't have it, U8, U9, 0, U10, U11, 0, U12, 13, 14, you bring all of them up there. Right, delete, not used anymore. So this is the thing. And that's gonna add up with this one, and it will turn out to be the following matrix. MULT, you multiply this with this one, and then you add it up with this one. Okay, there you go, you get it. You see, this is a very small quantities, number 4, because you don't apply force at the degree of freedom number 4. Degree of freedom number 5. Okay, I zoom in. 4, 5 is at the hinge. We don't have applied force at the hinge. Number 6, nothing, no moment apply there. Apply moment means the externally apply moment, not the moment from the spring. Okay. Number 8, it's nothing there. Now 19 is the reaction, match well, moment, nothing apply at the 10. 17 match well, and then rotation or moment, no, nothing apply there, and at the free end you don't have the externally apply force and moments. So it also works this way, but you will not know individual what's going on individually in each member. Okay, yeah, it's a good point. It can be done. And so, well, we finished ahead of time. Actually, we wouldn't supposed to have this class, right? Because it's not a scheduled class, but I just found that the room is unused in the morning of Tuesday, and I feel like, well, we should use the opportunity. So I will upload this file on the drive, so you can download and take a look inside. Also, the video will be uploaded very soon today, so you can proceed with your homework. So enjoy the rest of the day. Yeah, see you on Thursday.